let's look at another example of finding eigenvalues and eigenvectors. So this, we can tell just at the start that this example is going to be trickier because our matrix is 3 by 3, and so our characteristic polynomial will have degree 3, and so we might have as many as 3 different eigenvalues. And of course each one will have an eigenspace associated with it, right, an eigenspace full of eigenvectors. So right, we're going to have to do, if we end up with 3 different eigenvalues, we'll have to do 3 different row reductions to get our 3 eigenspaces. But that's life. Let's go ahead and find the characteristic polynomial so we can find the eigenvalues. So right, we're going to solve the equation 0 equals the characteristic polynomial. So 0 equals the determinant of, so I'm going to write out lambda I minus this matrix. So lambda minus 1, 0, 1, 0, lambda plus 1, 0, minus 1, 0, lambda minus 1. Okay, now this is a 3 by 3 determinant, but there's a row that has 2 zeros in it that we can expand across. So let's see, remember our cofactor, across the second row, our cofactor signs are going to be minus, plus, minus. So we only need to write down this middle one, so it's lambda plus 1 times, and then we do the determinant of everything left over after crossing out that column and that row. So we're going to get lambda minus 1 times lambda minus 1 plus 1. Okay, so this is lambda plus 1, let's see, 0 on the left-hand side, lambda plus 1 times, we're going to have to multiply this stuff out, so lambda squared minus 2 lambda minus 1, plus 1, plus another 1. Okay, now we could multiply this out, but remember, we're trying to set this equal to 0 and solve, so we want this factored anyway. Here it is partially factored, so we don't, multiplying this out would actually get us further away from solving this equation, not closer. So we know that lambda plus 1 has to be equal to 0, so that gives us a single eigenvalue, minus 1. And then also we get lambda squared minus 2 lambda plus 2 equals 0. And this equation, well, it's quadratic. It doesn't seem to factor, so we can use the quadratic formula. So we get 2 plus or minus the square root of, let's see, 4 minus 4 times 2 times 1, so minus 8 over 2. So 2 plus or minus the square root of negative 4. And like, this isn't real, but it does make sense as a complex number. So this is 2 plus or minus 2i over 2. So this is 1 plus or minus I. Okay, so this eigenvalue came out to be complex. And that tells us a couple things. Well, one main thing, I guess, which is if you have a vector with real entries, which is what we usually, right, what we usually do, there won't actually be any vectors with real entries, so that when you multiply it by a, you get a complex number times v. That's not going to happen just because this matrix product is a bunch of multiplying and adding, but if you start with all real numbers and you do nothing but multiply and add, you're never going to get complex numbers. But what this is telling us is that right, every direction corresponding to an eigenspace is sort of a special direction for that matrix. What this is telling us is that there actually aren't as many special directions as we might hope. Right? Since 2 of these eigenvalues are complex, we'll be missing 2 special directions. So this matrix only has 1 special direction, it turns out, and it's the one that corresponds to the eigenspace corresponding to, or the eigenvalue minus 1. So let's find this eigenspace for minus 1. So remember, what we're going to do is find the null space of a minus lambda I. So we need to, looks like we need to add a minus 1 to the diagonal elements. Sorry, add 1 to the diagonal elements. So that's 2, 0, 2. Let's see, a 0 here, minus 1, 0, 0, 0, minus 1. Oh, plus 1, sorry. Let me make sure I got that right. Yes. Okay. So then we'll do row reduction. So we can, let's see, why don't we use this 1 at the bottom to zero out the 2 above it. So we're doing, I guess we're doing row 1 minus 2 row 3. So 0, 0, minus 5. And then 1, 0, 2. And then across the middle we have all zeros. We could write down a solution just from here, but if we want to sort of put it into row echelon form, reduced row echelon form, we'd swap the 1, 0, 2 up to here, and then 0, 0, minus 5, but we can divide that row by minus 5 to get a 1 here, and then 0, 0, 0. Oh, and I guess we need to use this 1 here to zero out the 2 above it, so that's a 0. Okay, so here's reduced row echelon form. Now we need to figure out the collection of solutions to this. But the first row is telling us that the first entry of our solution vectors has to be 0. The second equation is telling us that the last entry in our solutions has to be 0. And since we have a free variable, that means the middle entry can be anything. And so in particular, the null space is going to be spanned by 0, 1, 0. Which makes sense, because if you look at the original matrix, right, if you multiply this by 0, anything, 0, multiplying by this matrix, the only place that your non-zero entry is going to hit anything is in this middle one where you get minus 1. So, right, this is going to give you 0 minus whatever that was, 0. And so, right, this is showing us very clearly that, that this is an eigenvector corresponding to the eigenvalue minus 1. Okay. Now, if we really want to, we can come up with an eigenspace for these eigenvalues, 1 plus I and 1 minus I, but we'll do 1. And it works exactly the same way. So we're just going to find the null space of A minus lambda I, capital I, right, identity matrix I. But in this case, this lambda is this complex number, right? So this is going to be trickier, a little trickier. So let's see. We had a minus 1 here. We had zeros here. Here we had a plus 1. Up here we had a plus 1. So plus 1 minus 1 plus I, that's minus I. And same thing down here. And then here our original matrix had a minus 1. So minus 1 minus 1 plus I, that's minus 2 minus I. Okay, let me make sure that I got that right. Yes. Okay. So now we're off into weird math land now because we have a matrix full of complex entries. How do we find the null space of this? Well, just do what we usually do. Just do row reduction. But the thing is, you can see that our scalars, right? Usually our scalars are just the real numbers, but all the entries in your matrix have to come from your scalars. But the entries in this matrix aren't coming from the real numbers. They're coming from the complex numbers, which usually mathematicians write this way. So as we do this row reduction, we'll have to use coefficients that come from the complex numbers. So in particular, we could multiply this first row by I to make progress on our row reduction. So that's going to make this first row 1, 0, minus 1. Sorry, 1, 0, minus I. And then 0, minus 2, minus I, 0. And then 1, 0, minus I. Okay. Now, to continue row reducing, right, we're going to need to do row 3 minus row 1. And then also, while we're at it, why don't we do row 2, divide it by minus 2 minus I. So 1, 0, minus I. The third row is going to turn out to be 0, 0, 0. So we are getting our row of zeros, right? Remember, when you're calculating an eigenspace, when you do this row reduction, you know ahead of time you ought to get a row of zeros, and there it is. And then in the second row, the only non-zero entry is the middle entry, and we're dividing it by itself, so it's going to turn out just to be 1. So like this. Okay, and now we need to write down a basic solution to this. This second row tells us that our middle entry has to be 0. And then the first row tells us that, let's see, we're going to need an I here and a 1 there. Okay. So the eigenspace for this eigenvalue is the span of the vector I0, 1. And now you see we're outside of our usual. We were looking for an eigenspace in R3, but what we actually got was an eigenspace in C3, right? Where it's a three-entry vector whose scalar entries are in the complex numbers. So if you end up with a complex eigenvalue, your eigenspaces are also going to have at least some complex entries. So in this example, we could, but we will not, calculate the eigenspace corresponding to 1 minus I, but it works out pretty similarly. So why is it that this particular matrix ends up having complex eigenvalues? Well, if you look back at this original matrix, if you concentrate just on these parts here, right, it looks like 1 minus 1, 1, 1. Right? There's some other stuff in the middle here, but this is kind of like a rotation matrix. In fact, this is a rotation matrix times the square root of 2. So part of what this matrix is doing in the x and z direction is some sort of rotation. And if you think about rotations, right, rotations in 2 dimensions don't leave any direction fixed. They change all the directions, and that means that there's no special directions for an eigenvector to point in, and so there's no real valued eigenvectors. So in the 2x2 case, you get complex eigenvalues when you're dealing with some sort of generalized rotation, and that's what is happening in the xz direction in this particular example.